Thank you, Ryan, for the introduction. I would like to present my master thesis project. Entropy predicts sensitivity of pseudo-random seeds, which I performed together under the supervision of Kristoffer Sahlin from Stockholm University and SciLife Lab. So when analyzing sequences and mapping and aligning them, the traditional way was doing a pairwise sequence alignment, but that's not feasible when looking at larger sequences, as the time complexity increases with the length of the sequence, like the product of the length of the sequence and the length of the query. So the most common technique in the so-called seed chain extend routine, which is performed nowadays in genome mapping and alignment, is typically done with k-mers, which are short subsequences from the sequence, which are then stored and matched. So if we seed a sequence of k-mers of length 30 for different mutation rates denoted on the x-axis, we can observe that already for a mutation rate of 5%, we are only able to cover around 55% of the sequence, while still 95% of the sequence is conserved, so we are not able to detect this dark zone, and this increases further in presence of mutation. So to overcome that, spaced and vector seeds have been developed, which are able to handle substitutions, but cannot handle indels that well, as can be seen in the second plot in the middle, where we have the fraction of indels on the x-axis. So 0% indel fraction means we have only substitutions, while on 100% we have 50% insertions, 50% deletions. And as can be seen here, at low indel fraction, we have really high sequence coverage, but roughly at 30%, we no longer have an advantage of using spaced k-mers. And then my supervisor recently published a new method, strobemers, which shows a high sensitivity, a high coverage for all different mutation profiles. But it was unknown prior to our study of what makes the seed construct efficient. So in our work, we designed new seeds, expanding the strobemer family. And doing that, we discovered that randomness makes seeds constructs more sensitive, and subsequently followed up by developing a model for estimating seed entropy that predicts seed sensitivity, which is better than the traditional trial and error when developing seed constructs. So traditionally, you would develop a seed construct, plug that in a common aligner such as Minimap, and test it there, which takes a lot of time and is also biased because you have a lot of parameters optimized in these aligners. And finally, we show that our new seed constructs work well for estimating average nucleotide identity, as presented earlier by David, and for read mapping. So first of all, what is a strobemer? So a strobemer is indexed by 4 different parameters, N, L, and a window. So instead of indexing one long k-mer, we are sequencing multiple shorter k-mers, which are then linked and sampled from a downstream window. So we would take the first position, take a shorter k-mer there, which is here of length 3, and then from a downstream window, characterized from an upper and lower bound, we are sampling a second strobe and concatenate them together. Yes. So in this example, we would link all the combinations together and find by applying a function that this combination should be chosen. And thereby now we have a strobemer consisting of 2 shorter k-mers with a flexible gap introducing randomness. So when we look at a short sequence with multiple mutations. And if we are seeding them with k-mers, traditionally, as we also have heard earlier in David's talk, whenever there's a mutation, all k-mers in this neighborhood are destroyed. So with rand strokes on the right, we can span over insertions and deletions and substitutions, and while we're still missing a lot of matches, by spanning over regions, we are at the end here covering almost the whole region from here to here. But we wanted to expand them further, so we came up with 3 new seed constructs. First of all, mixed strobes, which is a combination of k-mers and strobemers, which ideally have the benefits from k-mers, namely a high number of matches in conserved regions, while also the opportunity to match over insertions and deletions. And then we further generalized them in alt strobes, where our 2 strobes are no longer of equal size, but have a 2-to-1 ratio. And then further generalize that to multi-strobes, where we are sampling all different combinations of strobes. And while doing so, we observed that the more randomness we introduce, so in multi-strobes we have 2 levels of randomness, like the length of the 2 strobes and also the length of the gap. And we found that this is linked to a higher sensitivity, so we continued to find out why and how. So we started by modeling the seed entropy. And if you look at k-mers sampled at the blue position, we always know whether the downstream position, in this case the one denoted by the question mark, is covered or not. So there's no randomness. When we know for k-mer of length 4, a position 4 a basis downstream is always covered, but a position 5 downstream is never covered. And for rand strobes, we have these windows and have different opportunities. And so there's like a fraction which matches the specific position, and thereby we have introduced randomness and get a positive entropy. So when plotting the entropy for strobemers and k-mers, we can see that we have 0 for k-mers, and the longer the window is, the more options we have, and thereby we observe a higher entropy. So to explain it in a lot more detail, so we have for alt strobes on the x-axis the different length of the shorter strobes. So we could have like a combination of 0-30, that's k-mers on the left, and then 15-15, which is like the normal rand strobes, and we also wanted to explore everything in between. And we found some combinations, and namely especially 1/3 to 2/3, we observed a higher entropy than both for strobemers and k-mers. And the same we did for mixed strobes, where we have different combinations of k-mers and strobemers, and multi-strobes, where we have different length combinations. Now we have shown that we get some entropy, but this alone doesn't mean too much. So we also have to show whether entropy correlates with sensitivity, and with sensitivity we mean the possibility, or like the fraction that we observe at least one match in a short region. So if we plot entropy on the x-axis and sensitivity on the y-axis for all our different parameterizations, we can observe a good correlation between entropy and sensitivity, especially for larger windows. And entropy is quite easy and fast to compute, so it's a really nice and easy way to get a fast estimate on whether your seed construct is good or not. To show whether our new seed constructs work well, we implemented them in a very popular aligner Minimap 2. And for the indexing time, in the first column, we observe that we take roughly twice the time to construct our new seeds, but then when we align them in the second plot, we can observe a faster alignment, which scales up the more reads you want to align. And finally, we observe a higher fraction of correctly mapped reads when extracting the same number of nucleotides. But that having said, the results should be taken with a bit of grain of salt, because our constructs are not optimized for minimap, which is centered around minimizers with optimized parameters, and our entropy analysis didn't include any subsampling or doesn't account for that. So it should be taken as a proof of principle. Next, we set out to see whether our new strobe constructs are feasible for estimating average nucleotide identity, as been introduced earlier by David. And for that, we used an alignment-free method, which is called MASH, and was published by one of its colleagues in 2016. And first, we looked at how good we can estimate ANI based on simulated sequences. So we have the true mutation rate on the x-axis and our estimation on the y-axis. And we observe just visually that we have the best fit for k-mers. But interestingly, the ranks are better conserved in randstrobes and multistrobes. And that makes sense intuitively, because k-mers, or like MASH and ANI, is developed for exact seeds like k-mers. So we came up with introducing a scaling factor. And you can see once we introduce a scaling factor, we not only have a better, like the conversation of ranks remain the same, but you can see that the deviation to the true value has been shown by the total sum of squares is lower for randstrobes and multistrobes. And we observe that not only for this example, where we have equal amounts of substitution, insertions, and deletions, but this results hold true for all mutation profiles. Next, we confirmed our results on actual biological rates. So we took the correction factors from earlier, so we didn't fit them again to avoid overfitting, and estimate the average nucleotide identity on Oxford Nanotechnology reads of E. coli. And you can observe here that we have the best agreement between a gold standard reference obtained by in silico DNA hybridization, a tool called GGDC, which is known to yield best results when estimating sequence identity. And we observed the best agreement between multistrobes and this method, and also have the lowest sum of squares, the lowest deviation for multistrobes. So in conclusion, we present the first study on seed sensitivity analysis for seeds with a pseudo-random sampling decision, so reads where we have a flexible window, but just pseudo-random, because we still have to make sure that we are selecting the same reads, like the same seeds for reference and query. We followed up by developing a model for estimating seed entropy, which is fast to compute and can predict seed sensitivity. And this will be really useful for researchers in futures to develop new seed constructs and test them in a quick and unbiased way. Finally, we expanded the strobemer family by our 3 new constructs, mixed strobes, alt-strobes, and multistrobes, and provided a first proof of concept that they are feasible for estimating average nucleotide identity and can be used for read mapping. And in future, we want to incorporate subsampling into our seed constructs and also into our model to improve the model and use it to develop even better seed designs. And with that, I would like to thank my group, and especially Kristoffer, for being such a great mentor, co-worker, and supervisor. I would like to thank the funding bodies, and would like to thank my college, Churchill College at Cambridge University, and the conference organizers for providing me with travel fellowships to attend this conference. And with that, I would like to thank you for your audience, and I'm open to take any questions.